welcome to the second and final video in this topic of straight lines within the higher mathematics curriculum. Straight lines continued. Right, so what we're going to do in this tutorial is introduce three quantities which you can define for triangles, namely the median, the altitude, and the perpendicular bisector. And we're going to draw on many of the things that we know about straight lines to, in each case, work out the equation of a straight line for those three quantities. And for the whole tutorial, I'm going to actually just use the same triangle so that you can see all three things calculated for one triangle. And hopefully this will be enough information to both teach what the quantities are and also to give you some very good practice in calculating them. And the key for the listeners and viewers will be to then take other examples, maybe from past exam papers in wherever you live and wherever your exam board is, and to practice with this. So let me sketch the triangle that we're going to be using for this. It's one that I used in a tutorial privately just the other day, so I know that it will work pretty well for our purposes. So x and y, there's the origin, and I have a point roughly here. I have a point roughly sort of up here somewhere, and I have a point, way over here, about here. So we don't have to worry about exact values here. I'm just sort of sketching this for our purposes. Now I think I will use a ruler to draw the lines though, because there are going to be many lines on this triangle. And I think it would be helpful if I try to keep the lines that I draw relating to this triangle as straight as possible. Otherwise, there is a risk of disaster. Or let's say, that's too strong a term, a risk of lack of clarity, and which therefore is not good enough, because these tutorials are meant to be really clear. Right, good. So there's a triangle. Let me label the vertices A, B, and C. And let me indicate for each one what the coordinates are. So this one is at 2, 3. This one is at 8, 2. And this one up here is at 4, 7. So those are the x and y coordinates of those three vertices. Right, so the first thing we're going to look at is the median. Now, the median for a triangle is something that you can define for each vertex. So in fact, a triangle has three medians. Let's choose vertex C, and the line called the median from vertex C will bisect the opposing line, in this case AB. So if I just kind of eyeball this where the midpoint is, because again this is really just meant to be sort of a sketch, this line here will be the median. Let me draw that in red to distinguish it. So there's the median from C going through the line AB. And just to indicate that it's the median, I'm going to just put those little dashes there to indicate that we have bisected the line AB. Right, our job is to calculate the equation of the straight line of this median from vertex C. Let's call this midpoint here D, actually, okay? Well, we know that in order to evaluate or to calculate the equation of a straight line, we can either do it if we have 2 points, or we can do it if we have 1 point and the slope of the line. Well, let's see, what have we got so far? We have 1 point, but we have nothing else actually. So we're going to need to calculate something else before we can get at that equation of a straight line. And naturally, the thing that we can get pretty quickly is the coordinates of D, because it is the midpoint of this line segment AB. So the coordinates of D then will be the average of the x values of A and B. So I have 2 and 4, so I have 2 plus 4 divided by 2. And the y coordinate of D will be the average of the y values of A and B, which are 3 and 7. So the coordinates of D then are 3 and 5. Now, you could have gotten those a bit quicker by just looking at the numbers, but I'm just trying to indicate the method of calculating midpoint there, which we saw in the last tutorial. But fair enough. So we have 3, 5 as the coordinates of that midpoint. Very good. Now it's a piece of cake, because it's sort of National 5 sort of level now, because we have 2 points. We can just plough ahead. We can calculate the slope of that median. Let me call that line CD. Okay, so the slope will be the difference in the y values. So let me say it's 2 take away 5 is the difference in y, divided by the difference in x, 8 take away 3, and that is negative 3/5. It's good to do a little sort of plausibility check at this point actually, which is that having calculated the slope, does it look reasonable? Well, we're expecting something negative and relatively modest in magnitude, which this is, so it's plausible. Had we gotten either a positive number or a very large negative number, we would probably pause and say, hang on, maybe an error here. We have the slope, and now we can just use the following technique. We say that the variable y, take away, let's choose this point, take away the y value of that coordinate, is equal to the slope of the line multiplied by the variable x, take away the x value of that coordinate, which is 3. And if I just multiply this bracket out, I get minus 3/5 x plus 9/5. So the equation of the straight line that is the median from C is y equals negative 3/5 x plus 9/5, and then take this negative 5 over, plus 5. And just thinking of 5 as 25/5, I can add these together very quickly. So I'll have minus 3/5 x plus 25 plus 9 is 34. There we are. So that's the end of part 1. So we have defined what a median is, and we have calculated an example for this triangle. Another median, we're not going to calculate this, but just to show you, say the midpoint of AC would be about here, and the line that goes through B, and this midpoint would be the median for this triangle through angle B. Just to say something interesting about medians, 2 beautiful things. First of all, if you were to draw all 3 medians of a triangle, they all meet at the same point, which is very beautiful. And secondly, any median in a triangle splits the triangle into 2 equal areas, which is why it's called the median, which is a really beautiful property. Right, now the next topic is the altitude. Now, I don't usually do terrible jokes, but a terrible joke that just immediately springs to mind would be that if you were sick of doing straight lines, you might say you have altitude sickness. Very poor, I apologize. Now the altitude, let's do it again. Altitude is defined for each vertex. Let's do the altitude for vertex A, and the altitude is a line that crosses the opposing line at a right angle. Let me do this in green, actually, it'll stand out better. So here we are. Here's the altitude through A. And by definition, it cuts through the opposing line at a right angle. Okay, pretty good. Let's say that this point here is E, just so we have something to point to. So the altitude we're considering is AE here. Now, let's see. We know to calculate the equation of a straight line, we can do it if we have 2 points, which we just did when we were doing the median, or if we know the gradient and 1 point, we can calculate the equation of a straight line. Now, interestingly here, we don't know this point, and it's not going to be easy to get that point, but we can work out the slope of this line AE using the property of perpendicular lines, namely that the product of their slopes is -1. So if we calculate the slope of BC first, then we can immediately infer the slope of AE, and then we're on our way because we have that point A. We can easily get the equation of this straight line. Right, so the first thing we need then is the slope of BC. Okay, so it's a difference in y, which is 2 take away 7, divided by the difference in x, 8 take away 4. Now do notice this is just a kind of a trivial point, but it's worth mentioning. You might be saying when I say difference in y, 2 take away 7, you'd say, well, why don't you write 7 take away 2? Well, I could do that, but then I would say difference in x is 4 take away 8. To get the sign of the slope right, you need to be consistent that you always use 1 point as the point that you draw on first for your y and x values, and then the other point you draw on second. So I'm saying this take away this, and this take away this. So it looks a bit odd saying maybe difference in y, 2 take away 7, but it's just because I'm being consistent, always taking 1 point first. I always take the right point. So right point first, left point second. That way I can't have any error with the sign of my slope. And I get 2 take away 7 is -5 divided by 4, and that is the slope of BC. Reality check, yes, that looks okay. It's negative, it's bigger than -3/5, which it should be. So yeah, I say bigger in magnitude. So that's fine. Therefore, we can immediately say that the slope of the line that we're interested in, which is AE, is going to be 4/5. And why do I write that down so confidently? It's because 4/5 multiplied by -5/4 is -1. So the slope of the perpendicular line is such that its product with this slope is -1. So if you get a fraction for the first line, you can just invert the fraction and multiply by -1 to get the slope. And then it's just a piece of cake moving forward. We have the slope, we have a point on this altitude, so the variable y, take away this y value, which is 3, is equal to the slope of the line, which is 4/5, multiplied by the variable x, take away the x value of this point. Just multiply that out. We have 4/5 x, take away 8/5, and I can just tidy that up. So y will equal 4/5 x, take away 8/5, and then plus 3, taking that -3 over. 3 is 15/5, 15 take away 8 is 7, so this should be 7/5. And that's the equation of the altitude through A. And again, you can define 3 altitudes for a triangle, and again, they all meet at 1 point, which is different to the point at which the medians all meet. Finally, The third type of line that we can define for a triangle, actually there's a number of other lines, but for this for this higher maths syllabus, you just need to know about a third type of line, which is called the perpendicular bisector. Perpendicular bisector. Now, the perpendicular bisector is not defined for a vertex, it's defined for each of the three lines. What you can define for the vertices in terms of bisection are lines that bisect the angle, okay? But we're not looking at that right here. We're looking at lines that bisect sides of the triangle. So let me just, for the sake of variety, choose line AC, and I want to draw a line that is a perpendicular bisector. So I'm going to eyeball this because it is essentially a sketch. So there's, let's say that's the midpoint. Let me call that point F. And I want to draw a line, or draw it in blue, that is perpendicular. Okay. And that's the perpendicular bisector of the side of the triangle AC. I can define perpendicular bisectors for the other two sides, and no surprise, they meet at a common point. So very beautiful properties these lines have in triangles. Those points of concurrence do have names, but I'm not going to embarrass myself by trying to remember them because I always get them mixed up. But they have names like orthocenter and centroid and such, but I won't get them mixed up. I'll just refer you to the excellent Wikipedia pages on this topic where you can get all of that terminology absolutely correct. For our purposes though, we have to calculate this perpendicular bisector, where now we feel a bit bereft. We don't even have a point. Do we have enough information here? Well, yes we do, but we're going to have to work quite hard for our supper here. We're going to have to work out the slope of this line. Let me just call this perpendicular bisector L. I'm just going to call it L. There we are, L. The perpendicular bisector L. We're going to have to work quite hard here. We're going to have to calculate the midpoint of AC in order to get the coordinates of F, and then we can get the slope of L by calculating the slope of AC and then using our condition for perpendicularity to infer the slope of L, and then we'll have enough information to get the equation of the straight line that is that perpendicular bisector. So you can see why I left this one till last. There's kind of a bit more work to do for this. So first of all then we want to know the coordinates of F. That shouldn't be too bad. It's the midpoint of the line segment AC, and we have those coordinates, so it's going to be the average of the x values, so 2 plus 8 divided by 2, and it's going to be the average of the y values, 3 plus 2 divided by 2, so the coordinates of F are going to be 5, 5 halves. All right, so those are the coordinates of F there. Very good. And we need to calculate the slope of AC, from which we can get the slope of L. So the slope of AC is going to be the difference in y. 2 take away 3 divided by the difference in x. 8 take away 2, which is negative 1/6. Okay, I'm just going to do a quick check here. That looks fine. Reality check. Yes, it's negative. Yes, it's got really quite a small value. It's very shallow. Its magnitude is less than this one, as it should be. So that's very plausible. Good. Therefore, the slope of the line L, our perpendicular bisector, will be essentially -1 divided by this. The quick way to get that is to invert this fraction and to multiply by -1. When inverting the fraction, I get 6/1. Multiplying by -1, I get 6. So there we are, that's nice and straightforward. And that looks plausible, it's positive, and it's a very large value for a slope, and that does look just about right, doesn't it? Good. Now we're in business. We have the slope of our line, we have a point, it's just handle turning now. So the variable y, take away the y value of the point f through which our perpendicular bisector goes. So it's y take away 5/2 is equal to the slope, which is 6, multiplied by x, take away the x value of this point, which is 5. Multiply that out, I have 6x take away 30, and so finally then I have that y equals 6x take away 30 plus 5/2, and just think of 30 as 60/2, so I have negative 60/2 plus 5/2 would give me negative 55/2. Not the most elegant formula in the world, but that's the answer. Very good. So let me just label this triangle. It might help you in the future if you're referring back to this video. So this red line here was a median. And that was the first thing that we calculated. The green line we calculated is an altitude. And remember, the medians and the altitudes are defined for particular vertices, so we calculated the median through vertex C and we calculated the altitude through vertex A. The median bisects the opposing line, the altitude meets the opposing line at a right angle, and the final thing we calculated for one of the lines was its perpendicular bisector. I should say one of the sides of the triangle, to be a bit more precise, was its perpendicular bisector. Perpendicular bisector. Okay. There it is. So I hope this has been helpful. We've used one triangle for everything here. But, you know, this is something that you can really just have fun practicing. You know, you can just draw some old triangle with some coordinates and just spend hours of fun calculating medians, altitudes, and perpendicular bisectors. If you want a little challenge, what you can do is to give these points arbitrary coordinates and try to prove by calculating some medians that, for example, the medians intersect at a common point, or for the altitudes or the perpendicular bisectors. That would be something within your experience and ability level at this stage in mathematics. Quite challenging, but doable. So that might be something for you to try if you are stuck at home on a rainy day. With that, I'll end here, and we'll look forward to the next topic, which is going to be on quite a formal definition of functions. And I look forward to seeing you then.